So what I'd like to do in this lecture is to cover two models which will be algebraic embodiments of the abstract ideas that I've talked about in the first lecture. Obviously, because the way that they're going to be set up, they will be with loss of generality in many directions, and I'll try to indicate places where I think that the loss of generality is, from a theoretical perspective, problematic as opposed to an econometric one. Before I start, I did want to follow up on an issue with respect to this idea that environments with interactions can have these quote-unquote interesting properties, and add something relative to the talk actually that Larry gave. And that is, if one thinks about a kind of this line, this was a question came up, how do we interpret a line of agents or one agent's affecting the other, so on and so forth. One way to think about it is a model with local interactions would have said that the only way this agent can affect this agent is through this intermediary. So this agent affects this agent, affects this agent. So if I were to give an incentive effect exogenously to this actor, there's only one way it ripples through the system. And so if one thinks about that from the vantage point of Markov chains, that would basically give you sort of a geometric decline in the dependence across objects displaced by distance. Now contrast that from a world in which one says, and this is now the lattice in 2 dimensions, that where there's an idea that the actors influence each other directly that are one unit apart in distance, and ask the same question. In other words, how does this agent affect this agent? Well, as before, we would have exactly the same path as in the one-dimensional case, but now we can see indirect paths. In other words, this agent affects this one, affects this one, affects this one, and then has another effect here. And so one can work through the system, in other words, and see that once one alters the dimension, there's a qualitative change even with this notion of a two-dimensional, of a Markov process imposed in 2 dimensions. There's a qualitative change in the number of connections between the actors. And that's the key intuition as to why one can get quote-unquote interesting properties in environments in which we have agents that's displayed in space, displayed in 3 dimensions, so on and so forth, space and time. In other words, when one restricts oneself to a single dimension and then imposes this local structure, there's an implicit delimiting of the nature of the interactions, the connections across the actors. In contrast, as is evident from the 2-dimensional lattice versus 1, once we choose alternative configurations, richer ones, with respect, in this case, to dimension, the collective dependence in the system can qualitatively change. And so that is why one-dimensional models of magnetism, Isene's model, his thesis, did not produce a model of magnetism. It was the extension of the thesis to 2 dimensions by Rudolf Peierls that discovered that same idea of local interactions could indeed produce magnetism. And magnetism, remember, is just a statement that stuff's sufficiently dependent. It tips one way versus another. So the message of that, of course, is the actual choice of dependent structure will be essential for the qualitative properties of the system. Now, the good news is that there are broad classes of dependent structures, all of which give the same qualitative properties, such as the capacity, if there's sufficient interdependence, sensitivity to one actor to another, to cause a system to tip one way or another. And so in that sense, one doesn't have results that depend on the fine-grained details of this particular interaction structures, because obviously if we did, this would not be a useful theory. The notion of universality is that broad environments, broad classes of social structures give the same qualitative properties. And so issue number 1, or bottom line number 1, is that the mathematics of these environments will produce canonical examples in which one can get the sorts of phenomena I qualitatively refer to, multiple equilibria and the like. Bottom line number 2, these properties are typically quote-unquote universal, which is just jargon that says many different social structures for us in our language could produce the same thing. Bottom line 3, and this is just to follow up relative to something Larry said in the previous lecture, and that is the physical models have embedded in them various types of symmetries and the like, which are unappealing from the perspective of social structures. And so all atoms may or may not be or all atoms are surely created equal, but all human beings are heterogeneous. And so you have to respect that at the various levels in which one does the modeling. In terms of observable individual level heterogeneity, the way in which you model the unobservable heterogeneity across individuals, as well as the potential asymmetries and differential weights associated with social structures. Okay. So that was kind of some big picture background. What I'm going to do then is I'm going to present 2 models. The first model will be an example of the use of these interaction-based structures. What a shock, I'm going to pick one that I worked on. So, with my co-author Buzz Brock. I want to be clear that there's a set of people that, starting in the early 90s were working with these frameworks, and Larry was too modest to point out he was one of the real pioneers in all of this. And so there's a literature that'll be cited in the papers, if not directly placed on the reading list I gave for the course. I'm choosing this particular example for several reasons. One of them is I actually understand the model because I did work on it. And second, I think it illustrates some general principles. Okay? Final comment is it's a model that easily extrapolates, as it were, or generalizes to thinking about empirical work. So the idea is going to be that, again, I keep talking, it's going to look at interactions within a group, and it's going to take a very strong stance on the nature of the social interactions. As I've indicated, the universality property is a good hint for us. It says that you could relax that and get the same qualitative properties, but the goal here is to actually write out explicit equations to describe things. So the focus is going to be on an individual, on a single group G. And so the way to think about that is there's a population of individuals, and I'm going to make an incredibly strong assumption about how they interact with each other. Any social structure you come up with, I could always say there's one population, call that the group, and then have block diagonality if they don't interact, what have you. But nevertheless, this is going to be a strong assumption. These people are going to, in a very symmetric way, interact. Okay, as before, in sort of thinking through these problems, I'm going to start with a very simple description of choices. Okay, it's going to be so simple that obviously, once we have context, there may be many things that have to be included to do empirical work. So the thought experiment in general is going to be that I observe these outcomes, these choices of individuals, these omegas, and that there's going to be, as a tautology, they're maximizing something. So in other words, there's no content. Then I just say, I see some things that people made decisions somehow that was best for them relative to some payoff function V. Trivially, the function is going to depend on the choice, otherwise it wouldn't be much of a problem. The second is that there'll be something embedded in it which respects the notion that there's heterogeneity in the individual specific payoffs. I will call those HIs. In the segue to in the theory, I assume that we take as given those HIs and we condition the analysis on them. In empirical work, we assume they are observable modulo a finite parameter vector. That's just a fancy way of saying x beta, I don't know beta, but I have the x's so I can get the beta, so I treat that as that's going to become operationally observable. Okay, everybody with me? The third term is an epsilon. That's just a placeholder that says we will respect the presence of unobserved heterogeneity in the model. That's to keep the analogy to empirical work tight. In contrast to the h's, the assumption is we don't condition the analysis on the values. We will condition the analysis on the density. In other words, we have some characterization of the nature of the probability measures from which these epsilons are drawn. And what I will do is start by making a very strong assumption about it, and then I'll relax that. And then the intermediate term is where the action is going to be in terms of interaction, the social stuff, and that is each agent has beliefs about what others are going to do in the population, and consequently, their choices are affected by that. Now, I could have written this just in terms of expected payoffs, and if we were to start with a very explicit game theoretic formulation, that's exactly what we would have done. I would have been careful to say the information sets of the agents are knowledge of the structure of the environment. Each agent knows the H's. Each agent knows the beliefs of the other actors. That doesn't sound so great, but nevertheless, that's where we would start. In contrast, the private information is the epsilons. In other words, each agent knows his or her epsilon, but doesn't know the other epsilons, and that's the reason it becomes a game of incomplete information. Now, as Larry, as was pointed out, in some of the models, as you read them in the physics literature, they introduce beliefs, quote unquote, as an approximation trick. In other words, they set up a model and say that actually this atom depends on those atoms, it's too hard to solve, so we'll put in the expected values of the spins of the other atoms. In these models, there's no approximation or anything. The thought experiment is each actor has to form beliefs on which the decision making is done. All right, so right now that's that's kind of a very abstract way to describe social influences. Notice that the H's can have social components. In other words, everybody in the group could react to the average value of the parent's occupation or so on and so forth. So in saying, wow, I can have all of these types of interactions, some of them can have to do with some interdependence of the choices mediated by beliefs, others have to do with social context. Yeah, that all sounds wonderful. It's so wonderful that, again, the model's vacuous. Anything you say, any environment you describe, I could make up some description of this form. And so where the interest is going to be is how we make the with loss of generality assumptions and hopefully get a payoff. Please.
So just one point, and that is that you don't talk about it this way, but you could very easily just simply say that what you've described is a Bayesian game.
Yes.
And the equilibrium concepts that you're going to deploy, in some cases actually are Bayes-Nash equilibria, and in other cases are, and I don't know what you're going to do, so I won't commit yet, are closely related to.
They'll all be Bayes-Nash.
They all be Bayes-Nash.
Yeah. But I don't want to focus on the, this is a case where I'm really going to not, I don't want to say, it's important to do the game theoretic foundations exactly, but I just want to focus on the qualitative properties of the model.
Right, no,
Yeah.
I think, but I just want to,
Yeah.
I just want to say,
No, thank you.
this is not anything that is like so new that you shouldn't do it, because
Yeah.
no one will hire you. In fact, it's quite the reverse.
That's one of the things, actually, I'm very glad you said that. The use of these methods is no, you know, there's a number of people who say, oh, there's heterodox approaches to economics, some new paradigm. That's all nonsense. It is standard microeconomic theory, enriching it with ideas from sociology, transformed. I'm sorry to say we can't be as rich, but the sacrifices, or at least we try to get them into some sort of mathematically formal language so that the economic models begin to address ideas in other disciplines. Just as behavioral economics does not instantiate embed the richness of psychology, it takes ideas from it and tries to then link them to the formalism of economics. So in order to move from what I call the tautological description, we're going to begin to put some structure on the model, and the obvious one will be to assume that the beliefs exhibit some sort of self-consistency. If I have a model in which beliefs drive behavior and I don't impose any restriction on the beliefs, again, I could explain anything. You give me any data, I promise you, I'll give you a perfect goodness of fit. I'll pick the beliefs exactly right. And so in this model, I'm going to make the self-consistency assumption. And the reason the phrase self-consistency is used by microeconomists is because everybody sneers when they say, I'm going to assume rational expectations. But that's really what this is. In other words, it's saying that the agent's beliefs are consistent with the implied mathematical logic of the model. Now, I want to be two comments. Number one, I consider this a good modeling assumption as a baseline. I'm making no claims about the empirics per se as or as not valid. In other words, if I just said your agents are not rational in this sense, there's nothing to say. And so I think this is a useful baseline because, again, at least in the eternal dialogue of economic theory, it lets us think about the environment and understand what's going on. The more aggressive statement would be that I'm quite happy if you relax these rationality assumptions, but you have to tell me how. In other words, just say it is a model other than this one, again, makes the model tautologue uninteresting to us. So this assumption can be replaced with any other type of way to think about belief formation, but this is the one I want to focus on. Please.
How strongly do you need self-consistency rather than just some sort of coordination with, like, you can sort of change the slope of whatever your parameter, the observed interaction parameters are, and so forth, if you want to overestimate the impact of coordination or something like that?
Well, I think that the way I'm, assuming I'm processing your question correctly, is that you would like a dynamic model in which, as an example, the beliefs can be adapted, they can be overshooting, and the like.
Or a fixed point of something that starts from a dynamic framework or something like that.
That is in principle doable. I mean, I'm not going to do it here, and so it's a little bit, this talk is cheap. Do I see how you would set up the model? Yes. Do I want to make a claim that it's the same as this? Absolutely not.
Well,
Yeah.
actually done that.
Pardon me?
We actually did.
No, so we did I thought he had a dynamic problem, a different type of problem in mind. What Larry I did was we looked at the evolutionary game theoretic analog to this, where the agents there's noise and there's drift across the equilibria. That's one form of dynamics. Maybe I was misinterpreting. I thought you wanted.
That's what I was originally asking. So you can
so
then paper that.
No, we've done it, and so the message will be that in a static model where there's multiple equilibria, you have to ask different questions, like how long, what's kind of the time that you spend near each of the equilibria. That's question one. Question two is, if you're at one, how long does it take to get to the other? And so those become the new questions that sort of dynamic analysis allows one to address. And as I mentioned in the previous lecture, my view of poverty traps is that this deterministic view is just a theoretical nicety. Really, the relevant questions are mean first passage times from one set of configurations to a qualitatively different one. All right, so That's just a way of expressing what it means to say the subjective beliefs are self-consistent. It means that at those subjective beliefs, the conditional probabilities induced from the behavioral descriptions are in fact coincident with the subjective beliefs. All right, and so there was Larry's question. So that's kind of the background. Completely standard microeconomics with some effort to embed in ideas that we were going to call social, either because there's going to be something such as a conformity effect, a tendency for agents to wish to behave similarly to others because of a psychological primitive, or the idea that the environment in which they're functioning, there could be some sort of social aspect to marginal payoffs. And that would be something closer to the ideas one sees in growth contexts where there's spillover effects or something. And obviously I could go on, I could build in something about the tax structure and a public goods game. And all of those are compatible with the environment. So that's a very abstract thing. Now I'm going to be extremely specific because I want to give you an econometrically implementable model that has those abstract ideas. And so what I want to do is describe a multinomial logit model which has social interactions in them. And the way that it's going to work is that there's a set of capital L choices, and there's a choice-specific payoff for each individual. So the idea is going to be that individual I makes a choice L, and if he or she does it, there's a payoff. The payoff is going to be this, what I call the deterministic idiosyncratic component. Notice that it can differ across the choices. Obviously, if I eat vanilla, I get one payoff. If I eat arsenic, I get a different payoff. That's why there's an index by L. Don't look so eager to see for the data. Okay. The second idea is I'm going to allow each choice to have some unobserved heterogeneity associated with the payoff. Notice it's indexed by the choice as well as the individual. So the idea is there's something about your love of vanilla I can't observe. That's your shock. Your shock is for chocolate. Her shock is for orange sherbet, so on and so forth. I don't know the names of many ice creams. Okay, so that's going to allow for choice-specific and individual-specific heterogeneity. The final term is JPE of I, and that's the simplest way to talk about a social interaction, which is to say I derive utility based on the fraction of people that will behave similarly to me. In other words, make the same choice. So it's more fun for me if the people I care in my population come to SSI 2015, but since I don't know what they're going to do, I form beliefs about it. Right? I could rationalize that through some sort of model in which there's quadratic losses associated with the deviations of my behavior from others, as well as these marginal marginal payoff ideas. Okay. This is with loss of generality. With loss of generality, piece number one is the additive separability. Okay. It's the same, by the way, type of loss of generality for virtually every discrete choice model you've been taught, unless you took second-year econometrics from Rosa Matzkin, that was a reference to the UCLA students, or and learned about how to do a non-parametric analysis. But that's kind of the standard discrete choice language. All right, everybody comfortable with that? That's a very simple model. All right. So to say that I'm going to work with a multinomial logit model is to say that I'm going to take a stance on what the density is from which the errors are drawn. As a piece of theory, it's not interesting to allow I'll be honest with you. The interesting correlations in the errors would be an example of unuseful generality. So these are going to be errors that are independent across the choices. And this is where you get the bite in a multinomial logit. Each choice-specific error is assumed to be drawn from a doubly exponentially distributed density. That's an ugly functional form. We don't care about the functional form. There's only one thing I want you to see, which is there's a parameter beta. Beta indexes the thickness of the tails of the density. Now, it's a little bit annoying because if beta is very, very, very large, that means that the tails are narrow, whereas if beta is near zero, the tails are very fat. Okay, the choice of the functional form is useful to us for two reasons. Number one, it's useful to have a particular parameter that lets us index the nature of the unobserved heterogeneity. Because we could think about environments in which there's a lot of heterogeneity across the individuals and the stuff we don't know versus the stuff we know, and that turns out to matter for the analysis. Second, and this is why we love logit models, it turns out when I actually write down the conditional probabilities for the behaviors, I get things in exponential form, and exponentials have an extremely important property. They factor. And so it's easy to work out analytic solutions to them. Okay, if you said to me, what happens in this model if you assume provit versus logit, what I could tell you is nothing interesting changes. And in fact, well, I'll give you a theorem that says any density that has, which is continuous, will give qualitatively exactly the same properties. I say qualitatively because what will happen is when you start writing out theorems about the behavior of this environment, when you relax this functional form assumption, such as what is the name of the which density we're working with, the theorems become correspondingly less precise. And so, again, for a lowbrow theorist, which like me, the way I work is I have to write out everything as kind of parametric, the easiest thing, and then you can sort of try to figure out when you can generalize or not. So that's at least a approach to doing it. All right, so we have specified actually the entire environment. Think about it. All I said was each choice has a payoff. Each payoff depends on the expectations the agents have about the fraction of people making the choice. Let me finish. I've assumed self-consistency, so the condition to pin down the model is those probabilities will be, in fact, the ones that are true. And I've chosen the parametric density for the errors. Please.
I don't want to derail the talk, so 30 seconds is all I want. But if you've mentioned theorems that relate to different distributions, is there a place to look for those that you would suggest?
Yes, the Brock-Durlauf paper from which this is derived. So the way I'm sorry to sound cocky, but the point is what I'll do is it'll give the theorems for the logit case, then it will say assume there's any density with some smoothness conditions. To get rid of pathological cases, there'll be a set of theorems that are analogous to the first ones, they're just not as clean. All right, so remember I said that kind of the idea was that somehow we're going to let the micro give us conditional probabilities, and then we want to characterize the joint probabilities of the environment. Well, this is where the logit is our friend, and that is if I ask you what is the conditional probability that agent I makes the choice little l, given the things I've assumed the agents know, that's exactly the same as asking what is the probability that the agent makes a choice. It's exactly the same as the probability that that choice has the highest utility. And so that's just that's the standard calculation in any discrete choice model. You start off by saying, what are the conditional probabilities? Those are the things you want for likelihood analysis, right? And then what you end up saying is that is by definition the equivalent to the probability it was the optimal choice. And it's from that formula, that observation, that the multinomial logit is derived. And that is the formula for the multinomial logit, which is to say that the probability that I chooses L will equal e to the beta HIL plus beta J, that subjective probability, and there's a normalization, so the probability is summed to 1. Okay, that's it. This is the textbook introduction to logit models. What I want you to see is that in this environment now, if I was going to describe the joint probabilities given the stuff we condition on, because the expectations are mediating the interactions, that gives the conditional independence of the probabilities, and that's the reason why in other literatures the mean field approximation makes life easier, but for us, because of the information assumptions, which you may or may not like, if you accept them, says that is the exact equilibrium. Okay. So what's going to determine the probability of any set of choices I observe in the population? I need to know the distribution of the H's across choices and across individuals. That's the heterogeneity in the private incentives. And that's the heterogeneity that as I said, we sort of think about, we condition on it. This is what we could in principle learn from the data, and we want to know what the equilibrium looks like given that. The second thing I would need to do is tell you something about the values of the probabilities. That's already solved because we assume self-consistency. And then we have two other parameters. So we can think of the H's at the level of theory as a matrix of parameters, capital I times capital L. And we can think of the other two parameters as beta, that's the index for how much heterogeneity there is in the population. And then there's the J. Well, what is J? Well, that is the complementarity parameter. That's a sensitivity of each choice to what people think others are doing. Okay. And so in that sense, the model kind of has this clean description. There's a matrix of private incentives we have to somehow condition on. And then we have the two parameters that I treated as common across the actors. One was the heterogeneity from which the epsilons are drawn, and the other is the intensity of the complementarities. So if you said you want a richer model, what would that mean? It would mean that I would assign weights to other people. So in other words, rather than say I care about the just the fraction doing it. I might have an indicator function for every person in the population and a choice in individual specific weight. So if Larry does the same thing as me, that makes me very, very happy. I don't know some of you, so if you did it, I'd be pleased, but not insufferably so. And so that would be the idea that I could have, but it could be some things, if Larry does them, I don't care if he does them. Other things, it's very important, such as if he writes a paper with a co-author, it better be me. On the other hand, I'm really not interested in going bowling with him. So the serious point is the relaxation of, so the very strong assumption in saying there's a thing called J, which determines the strength of the social interdependences, that is the statement that the social structure has a form, that the only thing I care about is people making the same choice as me, and I don't care about their identities. I just care about the fraction doing it. To say that one wants a richer social structure, one wants to work with a sociomatrix, is to relax that. Now, even harder models, and these are sometimes in physics called spin glasses, would be to allow the J's themselves to vary across individuals. And so that could be a population in which you have some people that are, kind of iconoclast, they just do their own thing. The really cool models are when you have an interplay of positive and negative J's. I say cool in the sense that that gives very exotic properties. You could imagine an environment in which Scott, I want to be like Scott. Scott wants to be like Martha. And by the way, this is Martha Bailey who's lecturing tomorrow. I apologize I didn't introduce her. But Martha, seeing I have bad manners, really does not want to be the same as me. And so what happens in those worlds where there's an intermix of positive and negative pair-specific J's? Well, in the real world, we call it frustration, and that's what it's called in the mathematics literature. In other words, there isn't this, one of the advantages of the non-negative weights is that everything reinforces in the same direction. Frustration is when you want to be like one person, you want to be different than the other, but those two want to be the same. And so that's a hint that those models are qualitatively much harder to work with. They're examples in the physics literature, but I think they're uninteresting for social scientists because there's no theory about what's determining the J's as opposed to assuming they're normally distributed or something like that. And so if somebody thinks that's unfair, they should say so, but I think that is fair. But that's a completely open area. Please.
It's sort of a general issue that, like, if you allow the parameters to vary flexibly in as many dimensions as you want, you could sort of explain anything with copies of the parameters. Has anybody thought about trying to identify like the number of different groups or something? Could you imagine running a clustering algorithm to sort of find behavior similarities or something like that and sort of try and bin the groups that would have their own individual characteristics and somehow estimate the number of distinct J's in the population?
Actually, I think there's a bunch of good questions. Can I decompose that? There's a lot of great ideas there. Idea number one is that we might think that a way to extend the notion of social structure is not to say there's a group of people where everybody assigns the same weight to everybody else. Let's think about a classroom. All those of you, well, like not many of you, so the day that you have 5-year-olds, you'll discover something extraordinary. And that is boys play with boys and girls play with girls. I remember listening to a distinguished social network theorist who was using this extremely powerful machinery to look at interactions in kindergartens, and he after dropping an atomic bomb on it, discovered this fact. Okay, so what would that mean for a model? It would mean that I might want to say that rather than everybody reacts to the average, I might say people of the same gender react to each other with one weight, people of different genders act with a different weight. I could play that out with respect to ethnicity and a whole set of social group-specific markers. And in fact, for reasons I don't understand, I've asked some graduate students to do it, they just won't do it, but maybe I should be more aggressive. I think that one could take the linear and means models and generalize them in a very simple way, which is to say that people are members of groups. That's the memberships theory. And for each group, there's a linear and means effect. If you add those all up, what that would do is that would give each type an individual specific weight. And so the fact that, so Scott and I, we're both economists and we're both male, so he gets a weight. Now we're both economists, we're both male, and we have a third thing in common. I'm not going to say what it is. We get a bigger weight, okay? And so in other words, the point would be that if we could decompose social structure in this way of saying that it's kind of has a tree structure like that, that would allow for a parsimonious representation of heterogeneous J's. So that was one answer I wanted to give you. The second answer I wanted to give you was to say that a way to proceed would be to let J itself be functionally dependent on characteristics of the agents. So I could say the intensity between two individuals, I'm going to parameterize by some set of things that we think matter. Okay, and so that's how one could constructively proceed. underline your comment with something I think is extremely important, and it almost has to do with the philosophy of data analysis. What Scott asked is, what about doing a cluster algorithm to figure out something about the data? When I said that that's a philosophy of data analysis question, what he was saying is, I have a data set. Rather than say there is a model to fit the data, these observations, there's a prior thing I must do. I must study the data to determine what subsets of the data are appropriate for the application of a model. Okay? And that's really what a cluster analysis is, an example of an algorithm that asks that prior question. And so an example which I've personally worked on to excess had to do with this literature on cross-country growth regressions, where people take these 100 or so country panels and run linear regressions to describe everything from the poorest countries in the world to the most affluent. That's presupposing there is a model from which each country we think of as simply an observation that fulfills a condition called exchangeability, so that they're indistinguishable in terms of the underlying density that's generating them. A different question would be, analyze the data and tell me what countries behave similarly. In other words, it's appropriate to use a linear model for, and you'll be just absolutely shocked. If you take that approach, what you find is the poorest countries in the world obey one growth process, the richest countries in the world obey a different growth process, and at least in my own analysis, we end up with 4 distinct groups, and they're quite interpretable in terms of stage of economic development. So,
Not twin peaks, but peaks.
well, the peaks actually are, number of peaks is not determined by the model. There's a problem with the twin peaks analysis. That's offline. I could think about that in a micro sense, which is if I want to have models that are describing intergenerational mobility, is it natural to take very destitute, disadvantaged people and assume they're obeying the same linear model, let's be very concrete now, as extremely affluent families? One answer you could give is the world's probably nonlinear. A different answer would be to say we actually think that the environments in which people with very different characteristics are functioning would have different properties. So a question was brought up the other day asking whether or not, if one looks at the intergenerational mobility of blacks and whites, are the slopes different? And the question that was put on the table is, what about the intercept terms? That's a way of asking about that was your question, which is to say that there were 2 distinct models which are indexed by ethnicity, and because African Americans are experiencing different socioeconomic environments because of the fact they are African American. That's what discrimination would constitute, prejudice and other phenomena which are derivative from racial or from skin color differences. Okay. And so I think that idea is I'll be blunt, I think it's often underappreciated in particular empirical contexts. And so I'm glad you brought it up. All right, so back to this model. This is the really simple one. And again, life is incredibly simple. And the reason for that, there's only one thing to work out, which is what are the equilibrium probabilities of the different choices? The question I asked, and here I'm just assuming there's a lot of sufficient agents where I don't have to worry about finite sample approximations of the number of people in the groups. Am I doing that badly? Well, okay, I'll try to talk fast or less slow. All right, the serious point's the following. The guts of the economics, what makes this a Bayes-Nash equilibrium, is that each of the subjective probabilities is coincident with the probability generated by the model. So, and that's a trivial calculation. I have distributions of all the H's, the empirical distributions. So I'm just going to integrate with respect to empirical distributions. The probability Scott chooses something, there's some probability there. Probably Martha chooses, there's a different probability. There's a different probability for Larry, so what do? I average across them. The way you represent that is to simply say take the integral of the individual specific probabilities and do it across the population. That's an empirical probability measure, so de facto averaging. And that's the solution for the system. In other words, a set of choice-specific probabilities that are consistent with the individual choices. Okay? So that's a full characterization. Notice that could be taken directly to data. And what I mean by that is one parameterizes the H's with a finite, basically says we know H up to a finite dimensional set of parameters. That's what it means to say that I replace it with regressors and some coefficients. In any discrete choice model, of course, we normalize beta to equal 1 because you can only identify things up to scale. And then we would estimate the parameter J. So you can think about your standard logit model And you have to basically, and then you introduce these probabilities, but the probabilities are determined by those equations. So those are the side constraints in the likelihood. All right. So to characterize the equilibria, the way that I want to proceed is as follows. I'm going to just set the h is equal to 0. You can't do that in empirical work, obviously, because that's disrespecting the heterogeneity of the characteristics. I'm setting it equal to 0 because it'll clarify the properties of the model. So if I set the h is equal to 0, I went from my I times L matrix of parameters plus 2 to just 2. So in other words, the entire system is determined by the behavior of beta and the behavior of h. So what I claim is we can get very precise theorems in this special case. So what do I mean by that? Suppose that j were 0, there's no social influence. Then this would just, because I killed off the h's, now I would have a bunch of IID random variables for the choices. And it's a triviality to say, well, if they're IID, then I guess the probability of each choice must be for the individuals, and hence the population is 1 divided by L, the number of choices. So I've just given you the unique equilibrium choice-specific probabilities. Case number 2, sec j equal to infinity. Nobody can bear to be different from others. Well, in that case, I know the number of equilibria, there's L. Everybody chooses choice 1, or everybody chooses choice 2, or everybody chooses choice 3, ... All right, so in other words, we have the, kind of the obvious intuition. If I ramp the interdependence effect up enough, the complementarity, that forces unanimity of behavior. If it's not there, it reduces to a piece of algebraic trivia. Now, that gives us intuition that says that something about the strength of the complementarities is going to matter. That's ideal, comment 1. Comment 2, notice that in the model, it never said beta, it doesn't say j, it says beta j. So even though in the econometrics we do a normalization, the relevant parameter is going to turn out to be the product of the measure of heterogeneity with the intensity of the complementarity. And I'll come back to that. Comment 3, this sounds like a phase transition. In other words, I have this parameter j, it starts at 0, one equilibrium, and at some point, we know that as it goes to infinity, L equilibrium emerge. And so we're interested in the place where that happens. All right, so the specific theorem is this. And those errors are my errors. Okay, I'm sorry about that. The way that I thought I
What's
edited
the
these.
distribution of error?
When it says error reference source not found, it means that every paper that's been presented failed to cite my work adequately. No, okay, all right, I'm sorry about that. The theorem says the following. You take beta j, you divide it by the number of choices. If that's bigger than 1, that determines whether or not there's 3 equilibria or 1 equilibrium, or at least 3 equilibria. That's the whole theorem. So notice what it's saying. It says that it's the product of beta and j. We knew that had to be true. Why? Because if the tails are really fat, in other words, what's going to happen? The tails are really fat, then people are, because of the idiosyncratic components of their payoffs, that's controlling their behavior. There aren't enough people left over to self-consistently bunch. So that's why it's the interplay of the metric for heterogeneity, unobserved heterogeneity, with the intensity of the complementarity. So that's point number 1. Point number 2 is notice that the condition scales with the number of choices. So why would that be? In other words, why would it be that I need more complementarity, quote unquote, to get multiple equilibrium when there's 7 choices than if there were 1, if there's just 2? That is a problem with the intuition for it will also say something about a limit in the way I talked about the errors. I said the errors are IID across individuals and across choices. Well, now, if I have 7 choices, what's the probability one of those epsilons is huge? It's much higher than if I have 2 choices. And so there was kind of a bunch of simulation evidence on social interactions models. I kept finding this thing that the multiple equilibria kept disappearing when you had more choices. This at least tells you exactly why it's happening. Well, first of all, it gives you a theorem to explain how it would happen in a logit model, the exact, the scaling relationship. And 2, you can see what the intuition is. If I assume that individuals in a discrete choice environment are receiving these independent draws, that's increasing the probability of a draw that controls the behaviors. And that's really the idea which says the unobservable heterogeneity can swamp the other effects, and in particular the social effect. So what's the message for empirical work? It is, by the way, exactly the same message from the classical discrete choice literature. He said, when we are in environments, we have to think very hard about the error structure. And the classic red bus, blue bus problem arises. So in other words, if I said to you there's 3 choices, walk, red bus, blue bus, and I said the errors are independent, you would say, no, DeBrew has been there, done that, and we argued against it. That's why there are nested logit models. In other words, one has to account in many contexts for the fact that there's similarity between the choices, and the way we would model that is in something about the components of the associated error structures. So the theorem is mathematically correct, obviously, but the point is to say that it is derivative, the way I stated it, from the independence of the draws across the choices when we generalize it by allowing richer error structures of the type that drive nested logit models. Please.
So your intuition for why L matters is not just that, when L is large, there's a high probability that there's a big epsilon somewhere.
Mm-hmm.
It's actually that I think that the probability is large that there is a big gap between the highest epsilon and the second highest.
That's very important that he said that. Now, I was being sloppy. If the errors were correlated, then the gap wouldn't change. And so it was the independence plus the fact that I have multiple draws. So not only does that make the probability of one of the epsilons really big, it by implication made the probability of the gap between the two biggest very big. Okay, thank you. All right, so that's what I call a clean result. You get this exact scaling relationship. 2 parameters control the system, scaling between the number of choices and the outcomes. That's the benefit of using the logit. Now you might say to me, well, what if you relax that? Well, the way you'd relax it, and this is what I meant, you sort of start with special, go beyond. To relax it, if I drop the errors assumption, what I would do is I just say that there's some errors, and I still want to have something that kind of indexes whether the tails are thick or thin for the unobserved heterogeneity. So what I will do is take errors that come from any density you give me, as long as it's continuous, and I'll multiply them by beta inverse, and then I'll ask what happens as beta moves around. So I can basically set up the model in this way, and what it does, in other words, is it relaxes the logit assumption, but it preserves kind of the core idea that I had, or I was working with, which is there's an index for unobserved heterogeneity, and there's a parameter called strength of complementarity. So what will happen is you can go through, you can crank, you get more complicated ways one would describe the self-consistency condition, all that good stuff. And basically what happens is, remember before I had this very clean theorem that said beta j divided by L greater than or less than 1, that does everything for me? You get a weaker theorem. It says that for any choice of the densities under the smoothness assumption, it will be the case there's some threshold. I don't know if it's 1, I don't know if it's a billion. There'll be some number, I don't know what it depends on, such that you get at least 3 equilibria. And so that, in other words, you lose the clarity of the relationship, the nice scaling property, but and that's what I meant when I said you get the same idea qualitatively. It's still the interplay of the nature of the thickness of the tails, in other words, the amount of unobserved heterogeneity, with the strength of the complementarities. They combine to determine whether or not you get multiplicity versus uniqueness. And so messages I want you to get from this are, you can start with a very specific model and you get kind of these clean theorems, relax the assumptions. The issue is we look for is to ask whether the key ideas are being preserved with reference to the theorems. Okay, that's the whole theoretical structure. So let me make a couple of comments on the econometrics. First of all, that model is identified. And what I mean by that is, under the multinomial logit assumption, up to scale, all the parameters of the model are identified. That's result number 1. Result number 2, if the model only has 2 choices, so it's a binary choice model, think if you smoke, you don't smoke, you graduate from high school, you don't graduate from high school, that model is identified up to scale even if you don't know the density F. The state of the non-parametric discrete choice literature in these environments is that for binary choices, there's non-parametric identification and there's constructive algorithms for doing the estimation. There are no results for multinomial models with unknown densities. That's just where the literature is. Okay. Now, you were worried about endogeneity social structure. How might I do that? In other words, what I've actually described now is a model for multinomial choices with a particular type of social interaction. We have clear descriptions between the behavioral primitives, characteristics of the payoffs, the number of equilibria, and it turns out this environment is identified under the standard parametric assumptions that are used in any multinomial model, and we have the bonus proven in a different paper that it's identified even if I don't know the density for two choices. What I want to do now is just ask the question, how might I generalize it? Well, there's lots of directions, obviously. I would claim the obvious one is to try to endogenize the group structures. Now, that's hard business, but maybe a way to proceed would be to think about a sequential model in which there's a set of capital G groups. Agents first choose the group, and then conditional on the group, engage in a behavior in the group. Okay, that's a way to proceed, isn't it? Well, it is. And so all I want to do, because I do want to say something about the second model, is to make the observation. And the handbook chapter Larry and I wrote has this described, that if we think about an environment in which you have sequential logic choices, so first there's choices of groups, and then conditional on the groups, behaviors in the groups, all that does is give you a sequential logit model, and that's the description of the equilibrium, and one can compute the associated self-consistency conditions. I screwed up the indices should be G's and not N's, I apologize. But the point is that the language that was described initially, and as I said, this is kind of brought out in our handbook chapter, this becomes a model of endogenous social structure of a particular type, group structure, and associated behaviors within the groups. And so this model, even though we gave the characterization, we didn't actually analyze it. That's the thing we have to do next. Okay.
I'll get right on.
Yeah, get to work. Okay. All right. So you can, and so without going, so just to make a couple of comments about this, this can give many different routes to multiplicity, because there's going to be multiplicity not just because of what conditional on a group, a lot of complementarity. There could be multiplicity in terms of the choices of the groups and the associated equilibria that occur in the groups, because people have to form beliefs about what's going to happen. We'll have to say something about the beliefs about which equilibria prevail in the groups that are formed. And so this model actually probably would have an embarrassment of in fact, it clearly must have an embarrassment of equilibria, but again, it's written in a form that allows for empirical work. Right. Now, obviously, relative to a highbrow approach to game theory, there's all these functional form assumptions everywhere. The issue, which is not to say it's good or bad, is to ask whether they are worth it in terms of the segue between theory and econometric implementation. Please.
So a question about econometric implementation. So here you have some, you may not need to simulate the model because you have corresponding solution patterns. My question is how do you reach the data in the data? The model has multiple equilibria. You have to, like, do you know which equilibrium is playing in the data?
Two comments. Question number one is, your question is, does the presence of multiple equilibria inhibit identification? Interestingly enough, in these models, it facilitates identification. Now, how could that possibly be true? The way to think about it is multiple equilibria are emergent phenomena. They aren't properties of individuals, they're properties of the groups. So think about a world in which I already knew ex ante, the H's really were zero. Suppose that meant every group had exactly the same private incentives. This group is all ones, this is all minus ones, this is all ones, this is all minus ones. If that model's correctly specified, what's that going to have to give me under the logit assumption? Since I normalize beta equal 1, it has to tell me what j equals. In that case, infinity, because I said they're literally 1, but once I scaled back as to the fraction, that would, by implication, give me the value of j. Multiple equilibria create partial identification in environments in which there's a lack of complementarity between the agents. That's the work of L.A. Tamer and others. These environments, the multiple equilibria, because they're all emergent from the complementarities, they have every identification result that I've done never condition on the number of equilibria applied regardless. And that gave you the intuition as to why that would happen. Now, you could say to me that here's the worry, and that is high level, low level, high level. How do I know if these are classrooms, good teacher, bad teacher, good teacher? That's a statement about the error structure for the individuals in the group. In other words, you're saying to me, I don't get to assume they're independent anymore. There's a common component to the shock here, a common component to the shocks here, common component to the shocks here. Okay. There are techniques for dealing with that. And it turns out multiple equilibria are good for that in the following sense, and that is, The one thing teacher quality can't do if there's no social interactions is induce multiple equilibria. It has to be the J that does it. And so if I was willing to make an assumption, for example, that the distribution of teacher quality is monotonically shifting in the per capita income of a school district, if I observe a bunch of school districts that had higher values than, that were poor than the rich ones, even though I may not get consistent estimates, but I do get a partial identification of the intensity of the complementarities. It's not partial identification in the Mansky style, which is to say some probabilities between 0 and 1, and we shrink it. What would happen is you would end up with a statement that under these conditions, if you make this observation, one concludes that J is non-zero and it's big enough to produce multiple equilibria. So it's a different way to think about the notion of what partial identification means. I think a good way to think about it heuristically is you start off with a support for some object. Okay, if the probability is between 0 and 1, can the data cause the support to shrink? In the probability world for partial identification, we know the bounds, 0 and 1. No debates about that unless you're a quantum mechanic. And the idea is that you can then use the data to shrink the bounds. If it shrinks to a singleton, that's what it means to be identified. What happens in these models is there's economic properties that get revealed. And so what they do is they tell you something about the parameters relative to the logic of the model. Okay. So what I wanted to say is the following, and this is the second example, and I'm sorry that I'm going too slow. And that is I want to go through a model of neighborhoods, which kind of it's a type of group formation, but in this case, the logic of the model is entirely that residential neighborhoods form and they do something. Okay. The background to this is there's been a lot of talk in the media and in academia about something called the Gatsby Curve. Alan Kruger called it the Great Gatsby Curve. And it's an empirical observation, and that is that if you were to sort of look at a graph, as it were, of measures of cross-sectional inequality in national economies against their measures of intergenerational mobility, they seem to be upward sloping. So the claim, in other words, is that economies, societies, nations that have relatively narrow income distributions have greater mobility than societies that have a lot of cross-sectional inequality. In public policy debates, this is supposed to be evidence the American dream is a bunch of rubbish, because the U.S., the traditional story was, oh yes, Americans tolerate all of this inequality because we are so mobile. And by these measures, the U.S. looks both cross-sectionally unequal and relatively immobile. I will add, for the sake of being provocative, I think those types of arguments are not interesting. And what I mean by that, well, in fact, I said this last fall when somebody presented the data. I said, well, the problem in comparing Norway to the U.S. is Norway's filled with Norwegians. In other words, if you take an extremely homogeneous society and you have a scalar measure of mobility, how is that commensurate with a society which has people of all these many different ethnicities? I don't think from the perspective of the upward mobility of immigrants, one would say that Norway is somehow substantially more mobile than the United States. And so that is not to say that I turn a blind eye to the significance of decreases in intergenerational mobility or anything else. It's just these cross-country things are perilous. And it was really the same issue Scott brought up. You have to ask, prior to constructing a Gatsby curve, what are the countries that are appropriate to compare?
Exactly Matthew's criticism of the Gatsby curve, right? What was his comment? He said something that Greece is persistently less wealthy than Germany, right? On the other hand, and at the same time, Connecticut is persistently more wealthy than Mississippi, right? Why is it that we say that the Connecticut-Mississippi boundary is not relevant, but that the Greece-Germany boundary is relevant, right? That's essentially his argument.
But I'd like to think mine was different, that's all. Okay, so let's move on. So what I want to do is describe an environment, which is basically Becker and Tomes, which is the classic model of intergenerational mobility, written in social language. Okay, so economist version of social language. And so what I mean by that is the Becker-Tomes model as a theory of intergenerational mobility envisions a population of independent dynasties. Each dynasty it's an overlapping generation structure, so the idea is that each person lives 2 periods. In youth, one receives education. As an adult, one works, has a child, and then invests in the child. In other words, gives them education. And so the logic of those models, and of course there's a generalization that is a famous paper by Glenn Lowry, is that the inability of families to borrow against the future income of their offspring inhibits families with productive children, so to speak, who ought to be educated, from educating them. because the logic of the model would be that I borrow against my kids because they're going to make so much, I borrow against my kids' income. You let me pay for them to go to a college so that when they're adults, they'll make so much money that it was a good, quote unquote, an investment they could easily pay back. They would wish to pay back. Since I can't commit my children to pay my debts, that's basically the market imperfection. Now, whether or not one finds that interesting is not the point. What's key in these models is that they are family dynasty specific. The parents directly invest in the children out of the parents' budget constraint defined by income, and that determines the process by which incomes correlate between parents and offspring. All right? That's the entire logic of the model, and so it can be used to understand why when we get differing degrees of intergenerational mobility, depending on behavioral primitives, that would be one. Two, you can also get kinks in the model if you introduce various types of borrowing constraints that are a little less draconian than the one I just referred to, so on and so forth. And of course, if there was some lumpiness in the nature of the human capital, then you would get threshold effects. There's a minimum unit of you have to invest in order to produce a college education. So what I want to do is take a model like that and write down the social analog. And what I'm going to do is write it down with all functional form assumptions because it makes everything incredibly clean, and then I'll tell you why the assumptions matter. So in these models, the way to think about it, you've got these adults, these parents, they have this income. What they're going to do is they're going to consume some of it and they're going to invest the rest of it in their children. And so the simplest way to express that is to say they have preferences. They like consuming things and they like the kids. And so what is it they like about the kids? If I wanted to make the model hard, I'd say that they're computing the utility of their children and hence the utility of their grandchildren. That's not an interesting thing to do. I could say they just care about education. That's actually the Becker-Tomes assumption. In my capabilities advocacy, I care about my kids having big budget constraints, so I'm going to assume here, because it'll make life easy, I care about the income that my children have. That defines what they're going to be able to purchase. I don't take a stance on what they're going to do with the money, as evidenced by their career choices thus far. Okay, so now why do I want to make it a Cobb-Douglas assumption? Because that eliminates, that introduces a lot of linearity in the system. What it says is that when I have an income, I'm going to invest a constant fraction in my kids and a constant fraction in my toys. That's valuable to us because of the way in which I end up making the investment in my children. In the Becker-Tomes model, that's the key object to produce linear intergenerational elasticity regressions. Okay, so that's idea number one. Idea number two is that the way that the world works is actually, unlike the Becker-Tomes, this is where the only truly one of the substantive differences is I don't educate my kids. My community, my neighborhood educates my kids. No private schools in this world. And so what happens is each neighborhood generates human capital that the person receives as a child. It's linear, and there's a reason I want this function to be linear, and I'll explain in a second. And it's also multiplied by some heterogeneity, which reflects something about family-specific productivity. If you want to say it's genetic, you can allow correlation, and that again, that's not terribly interesting. Why do I want this to be linear? That's actually important. In this model, I'm interested in growing economies. In other words, it's one thing to set up, and this is actually what's done in a Lowry-type environment. There's a stationary distribution of income. And then you could ask about persistence in that environment. Well, for better or worse, even if it doesn't look like it's very high these days, the point is per capita income is growing secularly in societies, and I want to get calculations of the mobility dynamics against the background of growing per capita incomes. The easiest way to do that in this environment is to allow it to have some sensitivity, is to introduce a linearity in the production function, which is going to allow things to grow across time, that's all. And you might say, why is that a big deal? Because it turns out everything changes. It's one thing to say we have a world with a stationary income distribution, and I'm looking within this thing at the correlations of parents and kids. If the world has growing incomes, not only do you get different correlations, you ask different questions. I could ask a question such as, is it the case that one family dynasty, the ratio of their income to that of a less affluent family dynasty, never dips below the current level? In other words, it either stays the same or it keeps growing. That's an impossible phenomenon to occur in an economy without growth. And the reason for that is once you build in shocks, everything's ergodic, end of discussion. So growing economies actually have different notions of persistent inequality. All right, so that's the second idea. Third idea is that the shocks are going to have two components. I'm going to say there's something that's about the groups, the neighborhoods, In other words, some neighborhoods are usually good at facilitating education, others aren't. The second part's going to allow for stuff that's family specific. That just allows the neighborhoods to vibrate. Income, and this is what I meant by an investment, the way the world works is because everything's public in education, my income is not split between what I do for my kid directly in education, it's my consumption and the taxes I pay. Now for simplicity, I'm going to assume that the taxes are set by each neighborhood. So there's a vote, this determines the tax, and that is how the political economy works. It's very simple, but it's collective. In other words, within each neighborhood, there's a distribution of income. There's going to be some mechanism for producing equilibrium tax rates that collects all of the taxes and hence produces the educational quality for the children. Now this assumption, now notice two things. First of all, that's where the Cobb-Douglas makes life easy because everybody agrees on what the preferred tax rate. And the equilibrium concept is that a tax rate's in equilibrium, but there does not exist an alternative tax rate that would defeat it head to head in a vote. And so if everybody agrees on the tax rate, then we know what it is. Relaxation of that just creates some messes. And it's done in other work that I've written. Okay, so that's the political economy. Oh, I'm doing great. Thank you. I thought I was going to do it in 15 minutes. Actually, I'm going to finish on time. That's wonderful. If you
We were supposed to count the 15 minutes late we started rather than trying to cut you off after an hour 15, right?
Well, I certainly agree. Oh, but you're the one who said I was dictator, so I guess that's what's going to happen. All right, so, okay, I'll try to go as fast. I'm going to go as fast as I can. Well, actually, I won't, but I'll go faster. Okay. The thought experiment is you set tax rates, that creates a pool of resources. Those are the revenues. And those revenues are going to be converted into the human capital that's transmitted to children. Now, one question that arises in models in which you have endogenous neighborhoods is why doesn't everybody live by him or herself? In other words, why don't you have as many neighborhoods as there are people? Because after all, the richest family, maybe they don't want any neighbors. They're going to live in splendid isolation. So you have to build something in to do that. One possibility, and this is the standard one, is just to say there's 5 neighborhoods and a fifth of the population has to live in each one. The reason that I want to do something else is we do know that neighborhoods, school districts, these things evolve across time. And so one of the manifestations of increasing socioeconomic segregation would be missing if I actually obliged the neighborhoods to have fixed sizes. So the trick so what I'm going to give up on, I'm going to allow the number of neighborhoods to be endogenous, the size of the neighborhoods to be endogenous, but then I'm going to build in something that's clumsy to ensure that the neighborhoods don't fission into one upon population size agents. And so there's going to be some non-convexities in the production of human capital. In other words, it's better for my kids to be in larger groups than small groups. And there's lots of stories that I could tell that are not grossly implausible. I don't think any of them are particularly good, but that I just had to build something into the model to create incentives for families to have neighbors that are less affluent than themselves. And so there's going to be basically some sort of non-convexity in the production process. All right, human capital is determined the following way, and that is you look at the educational expenditures quality-wise that are produced by the neighbor and it gets multiplied by something, and that something is going to depend on the characteristics of the parents. The sufficient statistic for the parents in this case is their income. The average of the incomes in the neighborhood, that's going to capture something about role models. In a more if I was going to write this in my other work, there's a much more general functional form. It just depends on the empirical distribution function of the stuff in the neighborhood. It just makes things unclean in terms of the presentation of results. So the thought experiment again is going to be that this investment that's occurring in the kids in the neighborhood is being scaled by something that has to do with the role models and things like that, as well as something that's family specific. Again, notice the linearity. That's because I want the economy to grow. And I've already talked about political economy, and then there's only one question left. How do neighborhoods form? Because the way this model is going to work is you have a set of, remember, incredibly simple demography. It's crazy simple. Got a bunch of adults. They have incomes. Each one has a child. They're going to organize themselves into neighborhoods. Neighborhoods are like clubs. And so families move into neighborhoods, and the question is, well, what determines that allocation? So there are 2 possibilities to think about. One would be a core notion. In other words, in this world, families can actually choose who they live with. Okay. The other would be to say that each neighborhood has a set of prices, rental prices associated with it, and to say that the configuration of families in the neighborhoods is in equilibrium as no family wishes to move. It turns out in this model they give exactly the same answer. Now, is one to be preferred to the other? Well, you might say, well, we're good economists. Of course, prices determine things. Not so simple. And that, what I mean by that is if you sort of look at the history of segregation, both by race and by income in the United States, it's not just about prices doing it, it's about zoning. In other words, the fact that you have neighborhoods that ban multiple family dwellings, that's a way in which one zones to allow for the segregation. Now, I think a richer urban structure would wish to have heterogeneity in the units that define the neighborhoods, whether they're apartments, nice houses, et cetera, as well as prices. But I really want to put on the table that at this point, these models are not rich enough to do more than either look at core ideas or simply asking whether or not there's equilibrium prices. Please.
So I don't want to belabor this at all, but this is a very sophisticated version of the people model.
Yes.
And I am therefore surprised that you can get prices.
That's because of all the Cobb-Douglas stuff.
Ah, okay.
Yeah.
All right.
And it's because of the way I structured the complementary. It's Cobb-Douglas, which gives me the tax rates, plus it gives me, the complementarities give me a monotonicity relation. Willingness to pay strictly increasing in income in the model. That's sufficient for the existence of the prices. And that's kind of the general condition for the existence of prices to support income stratifications. You need the rich to be willing to pay more than the poor. That's how the rich, and that determines what the prices are to keep people separated. And so the model had enough structure on preferences to ensure that.
Right. Actually, that suggests something interesting to do, right? That no one's ever actually looked at lattice approaches to thinking about people models, and that's what you've got going on here. And that might solve a lot of problems from that direction, which is why it died.
And that's why you don't want to say this is a T-Bow model. All right. So the upshot is that I've given you a very simple environment, and of course I didn't even, and that is that I've just described how neighborhoods form. Families, are sort of subject to either price constraints or the core idea that people can are ending up isolated. So the first proposition is this model is extremely stratified. In other words, all the equilibria are stratified. Any configuration of families across neighborhoods must have the property. It's like taking the income distribution and, to quote Dennis Eppel, slicing it like a bologna. The richest tranches here, second, so on and so forth. Work by Eppel and co-authors relaxes that assumption in what I think is an interesting and important dimension. That's preference heterogeneity. So if one moves, go to where I used to live in Palo Alto, California, there were some extremely low quality apartments that were scandalously expensive. They weren't for graduate students. They were filled with immigrants who were spending 75% of more of their incomes just to be in the neighborhood because of the school district. And so I think that some aspects of mobility of the disadvantaged are not respected by not allowing for preference heterogeneity, where you have some overlap in the income distributions. But nevertheless, for the purposes of this model, that wasn't kind of essential. All right, and so what happens essentially is, so why does this happen? First of all, if you fix the number of people, I'm always better off if my neighbors are richer. Why? Because they have good spillover effects on my kids, and they pay more taxes. So once that's true, then I do the calculation that the willingness to pay is always higher for a rich person than a poor person for a given neighborhood quality, then I'm done. All right, so that's one proposition. Proposition two is that there always exists a core allocation of families. So what that means, and it's easier to talk about the core than price, it basically says if you ask the richest person who their most desired neighbors are, and make that the first neighborhood, you can show all those people they asked to join them agree. And they similarly agree they don't want anybody else in there. And so that's how you actually can construct the neighborhood structure. The Cobb-Douglas is important there, because if you and I agree on the taxes, then if a rich guy wants me, I have to want him. On the other hand, suppose we disagreed on the taxes. Then there could be some conflicts that say that I wouldn't necessarily want to add a rich person if they're going to set taxes that I find undesirable. Okay, there's ways to, other work I've taken care of that, but here I basically ruled that irritation out. Yes?
So based on understanding factors, so in setting up the end, there will be only one group, like the richest guy asks the second richest guy to join?
No. What I'm saying is the richest guy asks the second, the third, the fourth, and decides how many he wants. If he wanted all of them, then we'd be in the egalitarian utopia. But what's going to happen, the way the model's set up, is if the income inequality is great enough, there has to be multiple neighborhoods.
Then it would be like a perfect segregation.
Yes, this model, because it doesn't have preference heterogeneity, has perfect economic income segregation. All right, unsurprisingly, the sufficient statistics for tracing out any family's dynamics is you just simply have to know what the neighborhoods are and what the family incomes are. Those are the sufficient statistics, and so that lets me work out the stochastic processes. Okay, proposition 4 is the comment that I made before, and that is in guts of the model, you could say this is by the assumptions, obviously, on the way agents interact, I can eventually, if there's enough cross-sectional inequality, produce multiple neighborhoods. At some point, the implicit redistribution of rich to poor families associated with the tax system is going to create incentives for the richer families not to be living in the same neighborhoods as the poorer families. Okay. So the vision I want you to have is some cross-sectional distribution. If there's multiple neighborhoods, then they're stratified by income. And if there's enough cross-sectional inequality, the equilibrium can't be a single neighborhood. And that's of course, that has to drive the whole model. After all, once I have children in distinct neighborhoods, that's putting them on different trajectories. And so the only question left is what the trajectories look like. So, comment I made before about the Becker model, same thing happens here. The equilibria are the worst possible configurations for the poorest family. In other words, you ask what maximizes the gap between rich and poor. Lo and behold, of all the configurations, the equilibrium, please. This idea of an equity efficiency trade-off, I don't want to make the same claim I did about the Becker marriage model. But the phenomenon, again, is interesting that the equilibrium had this unique property. It was the maximized inequality at each point in time, defined as the endpoints of the support. There's one little technical caveat on neighborhood sizes, not interesting. All right, proposition 6 is there's nothing in this model that's generating efficient equilibria in terms of per capita incomes being maximized. That's obvious because of the spillover effects. Yes?
So if we were to have n number of neighborhoods that form, with the lowest income being...
I can't hear you.
If we were to have n neighborhoods that form from 1 to n...
Remember, the number changes every period.
yeah. So what would be the relative, like roughly the way you would think about what percent of income is taxed in the lowest income neighborhood versus the highest? Is there a modified relationship?
Well, remember, it's Cobb-Douglas. It's always the same. That's ruled out. Okay, and so again, this is a stripped-down version of another paper of mine. In that model, there's virtually no preference assumptions, which is why the theorems are all hideous, because they require a lot of caveats in them. So one thing that could cause convergence between rich and poor is if the poor neighborhood set a much higher tax rate than the rich neighborhood. So your intuition is exactly right. That's a mechanism that would work against inequality. Okay, and that, again, and so, hopefully what the paper, these papers do is it also indicates why these assumptions are useful to us. All right, proposition 7 now gets at something odd. And this is, remember I said these are growing economies, not just some static environment. What's happening in these models is if you look at the growth rates on average of kids, they're higher in the higher neighborhoods than the lower neighborhoods. Okay, that's because of the differences in the per capita investments and the spillover effects. Okay, just a consequence of, again, of the assumptions I made. So now we begin to get this is the one I wanted. I have a world in which you're getting differential growth rates across family dynasties indexed by the neighborhoods. And it's a growing world, it's not a stationary world. What turns out happens in this model is with positive probability, if I look at the ratio of incomes of the highest income family in this population, the lowest income family, that becomes a lower bound on the ratios of their descendants. So in other words, I look at the richest family and the poorest family. There's a ratio there. They're both growing over time, but I look at the ratio, it never decreases. But notice never decreases is not probability 1. It says there's a positive probability that will happen. Now, why is the theorem weak? It's because there's a bunch of heterogeneity built in there. Shocks are built in there. There's no reason to think any family can't have somebody of unusual talent. Bill Gates could have been born anywhere, so on and so forth. So what's happening in this model, and this is where the mathematics, it mattered that there was growth, is you have an environment in which you have these growing trajectories. And the question is, so what you do is I take the richest family and the poorest family. I take the difference between them. Everybody with me? Or I take the ratio of them, and I want to know whether or not it's ever going to hit the value 1. So that's the same thing as looking at the log of the differences and whether it hits 0, right? Everybody with me? So if I have a stochastic process, which because of growth, it's moving away from the origin, and that's what it means to say that rich families on average produce kids with higher growth rates than poor kids. It's a process where the growth is pushing away and creating more inequality between the descendants. Nevertheless, the sequences of shocks that the families experience could always drive them in the other direction. And so mathematically, the model is qualitatively the same as an environment in which you have a random walk with drift away from an absorbing barrier. And so if you ask the question, what's the probability a random walk with drift away from an absorbing barrier hits the absorbing barrier? That's the dynasty descendants equalize. The probability is between 0 and 1. And so what happens is that there's this force, this destabilizing force in the model in which the current inequality is growing, but there's enough stochasticity in the model that there's no notion of a deterministic poverty trap. It's just as the gap grows, it becomes less and less likely the descendants will reverse the relationship. So this is, obviously the model, I don't want to say it was rigged, it was engineered. It's called model design, not market design, to exploit the idea that along growing trajectories, you could ask a different inequality question, which is about kind of the ratios between agents, not about whether you've got just these deterministic traps, which would be an artifice of setting up an environment which imposed the stationarity. And so that was, again, when I said before that poverty traps are idealizations in stationary environments because they rule out any stochasticity, the idea that somebody of unusual sufficient talent is born and could break the poverty trap. That would be an easy example. Or I could give you some plethora of different types of shocks. Those are all, this model has a bunch of uncertainty and a bunch of stochasticity, and nevertheless gives us probabilistic descriptions as opposed to deterministic descriptions of poverty traps. Okay, and so the economics is very simple, and that is there are incentives for families to wish to be with, in this case, affluent neighbors. Affluent neighbors generate social influences, they generate taxes. Those those incentives, those are the kind of complementarities and characteristics. That's how I expressed them. And that was kind of the first proposition I put on the table in the first lecture. The second point is the presence of these effects induced incentives for segregation. The fact that others influence me tells me I have preferences over who they are. And given the way that things were set up in terms of the benefits of more affluent neighbors, that creates an incentive for the more affluent to isolate themselves from the less affluent. Once that happens, and you put it in this dynamic environment which allows for growth, you end up with these complicated trajectories, complicated in the sense that they aren't nice second-order stationary processes. They're complicated things growing, and that allows for, in this growing environment, permanent inequality to emerge in a way you could never have in a zero growth or in a strictly second-order stationary environment. And final comment. This model creates the Gatsby curve. In other words, what happens is you have enough cross-sectional inequality that increases the segregation in the neighborhoods, and that reduces the rate of mobility. Okay, this one's obviously trivially follows from the previous one, which is the whole action of the theorem, of the paper. So that, believe it or not, is all I wanted to say, and we are at 3 o'clock, so we're back on time. Okay, well, thanks for your attention. Okay, please.